Welcome everyone to our presentation. My name is Nick. My partner Chizoba and I will be discussing high-precision global positioning systems. Our presentation covers the basics of GPS in very intuitive ways, as well as introducing some more complex topics that increase the accuracy and reliability of it. So how does GPS work? Let's start with something more simple. Imagine being somewhere new and you don't know where you are, and you ask someone and they tell you that you are 880 miles from Sacramento. Well, that could be anywhere along that purple circle. Someone else tells you that you're 400 miles from Pierre, South Dakota. This narrows it down to 2 points, but how are you able to tell whether or not you're in Wyoming or Colorado? Someone else tells you that you are 770 miles from Austin, Texas. Using at least these 3 bits of information, we can affirmatively conclude that we are in Denver, Colorado. A GPS system would do something like this, but with more people telling you how far away you are and in 3D space. Luckily, there are 32 satellites in orbit able to tell us how far away we are from them. Given the diverse orbit patterns and directions, we are fortunate enough to have at least 4 in our line of sight at all times. We just showed you how it is possible to use 3 people to find yourself on a 2D map. The situation is the same for our 3D world, but a 4th satellite is needed in order to provide an accurate reading. Each satellite has an atomic clock on board that keeps an accurate reading of the time and is so good that it only loses 1 second every 100 million years. The accuracy of time here is important because signals that are being sent from other satellites are being received from very long distances and at the speed of light. These far distances and high speeds without a timestamp can and will result in a very large margin of error, up to 1 million miles. Although each individual clocks are accurate, they may not be perfectly synced up with each other.
What is considered the standard of GPS accuracy is being within 5 meters of your desired location. This is actually the technology that most mobile phones being manufactured today make use of. This margin of error of 5 meters is not very good, and we would like to correct that. But first, we have to take a look at some of the factors that are causing this error to begin with. Some of the factors that may be causing some errors include satellite internal clock errors, satellite orbit errors, receiver noise, reflections due to the very long signal travel distance. It is bound to bounce off of something, be it a tall building or another object. And lastly, there is the error caused by the signal going through the ionosphere and the troposphere, and that creates a delay. In our presentation today, we will be discussing 4 approaches taken to correct for these errors. The first one is called DGNSS, and this stands for Differential Global Navigation Satellite System. From our diagram, as you can see, there are a few components. We have a fixed base GPS receiver. This receiver knows its location and position very accurately. Next, we have the rover GPS, and that is the object whose location we're trying to accurately determine. We also have the satellites in space that you can see floating around at the top there. The way that this works is that the base uses PRN, which stands for pseudo-random noise. And this signal is used to measure the position of the base. So the base measures its own position via this signal. It makes use of the time in that it takes the time the signal originated from the satellite till the time it got to the base, and it multiplies that time by the speed of light in order to get the distance traveled. And since the base accurately knows its own location, it then uses the measured data that was obtained from the pseudorandom noise, and it uses that to calculate correction data. It's kind of like when you do percent error calculations in the lab, where you use the theoretical value and compare it to your measurements and get the percent error. So this percent error is similar to the correction data. So the fixed base GPS sends this correction data through a radio link to the rover GPS. The rover GPS then uses that correction data and corrects the measured data that it gets itself from the satellite, and a more accurate location of the rover is determined. For this type of GPS, it has an accuracy of being between 0.5 and 5 meters. The second method we're going to be talking about is RTK, which stands for real-time kinematics. Even though it's called real-time kinematics, it also has non-real-time applications, in that the data can also be recorded for later processing. So this method works very similarly to the DGNSS that we talked about just before. The only difference is that instead of the time taken for the signal to go from the satellite to the base, it uses the phase. And in our diagram, we represent that by using the squiggly lines, the kind of sinusoidal lines. So a signal is sent from the satellite to both the receiver and the rover. And the way this works is that the base counts the number of cycles completed by the carrier signal, and then measures the phase of the carrier signal. And the base takes this measurement of the carrier phase and compares it to its known positional data, and then it deduces the correction data from that difference. This correction data is transmitted to the rover GPS as it was before, and the rover GPS uses the correction data to correct its own measured data and determine a more accurate position of it. This method is about 1,000 times more accurate than the previous method, and it results in an accuracy of being between 2 to 10 centimeters, which is pretty good, especially compared to a high of 5 meters. So the third method is to use SBAS, which stands for Satellite-Based Augmentation System. In this, we have drawn 3 GNSS satellites, and again, GNSS stands for Global Navigation Satellite System. It also has something similar to a base station that we had in the previous methods, except it's not one base. It's actually a worldwide ground network of reference stations, and all their locations are accurately known. So it has a master station, which is also known as an uplink station, and it has a GPS rover, as in the last. So the rover is just what we're trying to determine the location of. So it uses 3 moving satellites, or we're showing 3 moving satellites, and 1 geostationary satellite. Geostationary means that the satellite appears to be stationary when you're observing it from a certain point or a locus of points. So how this works is that the GNSS signal is sent from the reference station to the master station. The master station then calculates wide area corrections, because this is a network of stations and not just one base station. These corrections are uplinked to the geostationary satellite. The SBAS satellites beam the correction data to the rover, and this results in an accuracy of between 0.6 and 2 meters. The next and the last method is PPP, which is short for precise point position. This is pretty similar to SBAS, which we just talked about, in that it uses a network of accurately located stations, but it provides greater accuracy. So how exactly does it do this? First, it corrects for tropospheric delays, and these errors occur when passing through the troposphere. It also corrects for the Earth's tides effect by using theoretical models of it. Another way it improves the accuracy of the SBAS is by using dual frequency carriers to better correct for the ionospheric delays. Another way it provides greater accuracy is by using external satellite orbits, and that corrects clock errors. It also makes use of an EKF, which is an extended Kalman filter, and it uses this to estimate all measurements and reduce the signal noise. The accuracy of this type of correction method is within 10 centimeters, which is pretty impressive.
These types of GPS systems are similar in some ways. For example, when comparing differential GPS and real-time kinematic GPS, we can see that they both require precisely known location of the base station and a strong transmission link from the base to the thing that is being tracked. However, RTK is more accurate because of its use of phase data when tracking the location. The signal from an RTK satellite is sent at a very high frequency, which allows us to take more frequent measurements of the signal, resulting in closer wavelengths, somewhere on the order of 10 centimeters. The other two systems, satellite-based augmentation systems and precision point positioning, are fundamentally the same, both using a system of base stations and geostationary orbiting satellites. However, due to the complex programming of the PPP system, the accuracy is way better when compared to SBAS. There are different scenarios and applications of GPS other than finding your way to Starbucks in your pajamas, but in any circumstance, it is important to have a high degree of accuracy. It turns out that RTK and PPP both have high degrees of accuracy, but require different processing power. RTK is good for small local applications like construction or surveying, as long as the rover is no further than 10,000 kilometers away from the base. PPP has applications in robotics and autonomous driving because of its high demand for processing power, where robots and artificial intelligent machines already have strong onboard processing power, so the convergence time is shortened.